So, what the chain rule looks like, or how it is used, is on a composite function, a function where you have a function embedded inside of another function. We saw that when we would do something like f of g of x. Do you remember doing that? Mm-hmm. Okay. That's the kind of function that I'm looking at here. So I'm going to write it with the ones that we're used to doing. So my function is f of x, and it is a composite function of g and h. And so it looks like g of h of x. The product rule and the quotient rule, product when I have two polynomials, I can actually use it for more, 3 or 4 polynomials even. I have like a little saying for first to second plus second to first. The quotient rule, low d high minus high d low over low low. Chain rule, I don't have anything for. I just kind of remember how it goes, and I'm sorry, and I just never came up with anything. But this is what the derivative looks like. Okay? It is the derivative of the outer function, leaving the inner function alone, times the derivative of the inner function. So I have to take the derivative of both functions, but I do the first without touching the inside one, or the outer without touching the inside, and then I do the derivative of the outer. And so it's a little bit hard sometimes to wrap your head around when we look at this, because it's hard to distinguish the outer versus the inner. But if I look at a problem like number 1, scan this down a little bit. Problem like number 1, my outer function is just the fact that I am raising something to the 5th power. My inner function is the polynomial that's on the inside. All right? So when I'm doing my derivative, if I think in my brain, this is my brain thought, if I were to take the derivative of x to the 5th, I would multiply the 5 in front, and I would lower the power 1, right? That's just a power rule, a basic power rule. That's what I'm going to do, except for the 5th power isn't on x. It's on this big old parenthesis. So I'm going to bring the 5 down. I'm going to lower the power 1. But again, the 5th power is on what's inside of there, 5x cubed plus 6x plus 4. That's the derivative of the outer. Now I'll do the derivative of the inner. And I don't do a whole lot of cleanup on these, because it would be ridiculous for me to have you take this to the 4th power, or some of the functions that we have to the 4th power. You would spend easily a half hour or more just trying to sort that out and distribute all of those, and at some point you're going to drop a sign, so just leave these. Leave it as is. You don't have to touch it, you don't have to do anything with it. Sometimes if there's something easy to do, like I have an end number and a front number that I can multiply pretty nicely, go for it, but normally you don't have to do that. So I would just leave this as my final answer. Yes?
So with the 5x cubed, would it stay cubed, or would it put on the squared?
In here it stays cubed. When it's inside it stays cubed, but in here when I do the derivative of the second part, it lowers it down to a squared. Yeah. It doesn't make a difference if I have negative powers, fraction powers. I do the same thing. In this case, for number 2, my outer function is the fact that I'm raising something to the negative 4th power. And so to do my derivative, I multiply the power in front, and I lower it 1. Remember, when you're subtracting from negatives, it's going to get bigger negatives, so negative 4 minus 1 is negative 5. Again, This power isn't on x, it's on this polynomial function, so I'm just going to write that on the inside. And now I'll address that polynomial function. This particular problem might be a time where I would do the slightest amount of cleanup, because it's pretty easy for me to multiply 8 times negative 4, and then I can just leave that negative 5th power on the outside. I have also seen people address the negative power by bringing it down to the bottom. It is easier to evaluate when we have a positive power, and so when I'm evaluating, I will always bring that down. Make it positive because it's easier just visually and easier mathematically for me to figure out what that equals. But if you're doing your derivative and you leave it like this because we're not plugging anything in, fine, I don't care. So both of these answers are totally acceptable answers. One is not better than another. The top one is a little more streamlined to look at. The bottom one is a little bit nicer to do the math on if we're going to actually find the slope at a point. Okay? All right. What if I have a radical function? We've done square roots before. So what if I have a radical function? Remember, again, here's me thinking. This is my little think bubble. I'm thinking here. I'm thinking. The square root of x is x to the what? Power. 1/2. Beautiful. The cube root of x is x to the 1/3 power. The fourth root of x is x to the 1/4 power. You get what's going on. So the cube root of this polynomial is the same as 4x to the 5th plus 1 raised to the 1/3 power. So anytime we see a radical, instead of dealing with it as a radical, where when we did it with the definition of the derivative, we had to apply the conjugate and things got a little bit messy and then it cleaned up eventually, but all we need to do is write it as a power and then apply the derivative as normal. So again, if this were x to the 1/3 power, my derivative would simply be 1/3 times x to the negative 2/3 power, because 1/3 minus 1, remember I always lower my power 1. But again, it's not on x this time. It's on this polynomial. So I have to address that polynomial as well in terms of derivatives. And I'll multiply it by the derivative of that. Again, most of the time I would leave this like this. If I were going to evaluate it, I would do the 20x to the 4th up on top over the 3 from the 1/3, because that's in the denominator, times the cube root of 4x to the 5th plus 1 squared. Again, if I were going to evaluate it, I would rewrite it like this. Sometimes even you'll see it in a rationalized denominator form, but that gets more into your calc time. But right now, again, I'd probably leave it like this as my answer. Put it in this form if I'm trying to figure out what it equals. Because then I can plug in a number pretty easily. I get a numerator, I get a denominator, I get a fraction. Again, either answer is fine. One is not better than the other. It just sort of depends on what you're doing with it. please give number 4 a try. See how you do. I wrote it both ways just in case somebody was like, I just want to see if I can do that. But I'm sure most of you left it like this, am I correct? Yeah. Because that's just kind of, as long as you can kind of go through and do it. Some of you will just probably, when we are evaluating, plug it into your calculator anyways. But how did we do? Did everybody do all right? Feel okay? Anybody have a question? Anybody got something to say? Say it. I can take it. Okay. Everybody good? Okay. All right. So, of course, what comes next is our trig functions, because we don't want to let those go. In pre-calc, we see those a lot. And the chain rule is applied on the trig function because when we are doing a trig function or working with a trig function, the sine of a value or the cosine of a value, the sine and cosine are actually a function. And then what the angle is, if we have a variable in there, is our other part of a function, okay? So when we have sine and cosine, we have to apply the chain rule. But how do we figure out what the derivative of the sine and the derivative of the cosine are? It is a little bit of a challenge. But what we can use is something called kind of a slope field. Or what we're going to do is we're going to approximate the slopes on the sine function and then turn those slopes into a tangent, because the derivative is the slope of the tangent line. So if we can get the slope of the tangent lines, maybe we can convert it into a function that we can use for a derivative. So what I'm going to do is my best picture of a sine function. And here's what my sine function looks like. There's my... We always started with 4 little tick marks. Does that ring a bell? Yep. And then it's just sine, so it tops out at 1 and bottoms out at -1. And I could put all those angles in there. 2 pi was the last tick mark because that was 1 lap around the unit circle. But for what we're doing today, it's not necessary. Okay? So I'm going to sketch my sine. My sine looks like this. I always do the 5-point method of graphing. It starts at 0. And then I sketch my graph. And it goes on and on and on forever, but that's what I've got good enough. Okay? What I'm going to do is I'm going to try to approximate the slopes. And I'm going to start at 0. At 0, what does that slope sort of look like maybe? It's pretty even keeled, right? Positive. Anybody got a guess? Sort of depends on how steep you drew your picture. On my picture, is 1 fair enough? Slope of 1, my slope right here looks like maybe 1. Okay. Then I'm going to go at pi over 4, or sorry, pi over 2. That's my first tick mark at pi over 2. I'm going to take that point and I'm going to draw the slope of the tangent. That one's much easier, isn't it? There's not much else I can say other than what my slope is. Flat line, 0. I've got a slope here of 0. Okay. Again, I'm going to approximate my slope, and I'm going to go to my next point of interest, and I'm going to approximate the slope about here. Again, not super easy. It depends on how you drew it, but it's negative for sure. It's not real steep. It's a pretty average looking negative slope. I'm just going to go with -1. Again, I'm just approximating. It doesn't have to be perfect. And if you're looking at it and you're like, man, mine looks like -2. Great. It's not gonna hurt what we're doing, okay? Then I'm gonna go here. What's my next slope? Yeah, that one's pretty easy again. And then I'll go to my last spot. What does my last slope sort of look like? Really looks like the first slope or the first part of the slope. And this is going to repeat forever and ever and ever and ever and ever. Okay? So I've got some points. I'm going to make a new graph and I'm going to plot my slopes. I'm going to come over here. I'm going to make a new graph. And at 0, it looked like my slope was something positive. I chose 1. At the first tick mark, it looked like my slope was 0. So I chose, made it look flat, was changing directions. And then at pi, it looked like my slope was -1, so I'll plot that down there. And then my next slope looked like it was 0 again. And my last slope looked a lot like the first slope. And if I connect this function, what did I create? Cosine. So if my slopes all match up to be the graph of cosine, that must mean my derivative of sine is cosine. So if y is sine of x, like we were given, then dy dx is the cosine of x. So it seems like it would make sense then that the derivative of cosine is probably sine, but let's go through the same process and see what happens. So I'm going to start with a cosine graph. I'm going to make my 4 tick marks. I'm not going to get too crazy about numbering anything because it doesn't really matter. I just want to approximate the slopes. And so here's my cosine graph. And let's start taking key points and finding slopes. How about this top point? If I draw a tangent to that top point, what is my slope? 0. If I draw a tangent to this next point, remember it's a line that just touches that next point, what does it look like? Sure does. How about this low guy? Looks like 0 again. This one could be pretty close to 1 maybe. And my last one is 0 again. All again I'm doing is I'm approximating the slope because that's what a derivative is. The derivative is the slope of the tangent line. If I figure out the slope of the tangent line, I can get approximate values on a graph. So here I go. It started with 0, went to -1, back to 0, up to +1, back to 0. Is that a sine graph? No. Kind of. Shifted. Flipped. Yeah. In fact, it looks like it goes in the opposite direction of what a sine graph would go. Or it is shifted over to the right, but we're going to go with the opposite one. So if y is the cosine of x, then its derivative is the opposite of the sine. That means I flip the sign over. Instead of going up to 1 at pi over 2, I go down to -1. And so there are my sine and cosine derivatives. Now these were the derivatives when I just had x, just a regular old function I just put on there. But because all of my derivatives here on these bottom ones, or all of my functions have something other than just x in, I'm going to have to use the chain rule on them. My outer function being the trig part of it, My inner function being the angle that I'm taking the trig function of, okay? So, this is the sine of 5x. I start with my derivative just like before. The outer is the sine, the inner is the angle that I'm taking the sine of. So I start with the outer. What's the derivative of sine? Cosine. I leave the inner as is. But I have to address that inner value being something other than just x. So I'm going to multiply it by the derivative of 5x, which is 5. When I do these, I like to bring the number up front away from the angle. Is it the law? No. Do I want you to do it? Yeah, I do. It's not that difficult to do. That just separates it from what we're taking the cosine of. So I'm multiplying 5 times the cosine of 5x. Bless you. F prime of x on my next one. I take the derivative of the cosine, negative sine, but I don't touch the inner part of it, the angle. Then I will address that polynomial on the inside and take the derivative of 3x to the 5th, 15x to the 4th. I do a little maneuvering just to make it easier on the eyes. And there's my derivative. Again, that whole 15x to the 4th part of it, that's the chain rule in action. I do the derivative of the fact that I'm doing a trig function, sine or cosine. It's going to be the sine or cosine of whatever the original function was on, but then I have to apply for that original function being something other than x, so that's my derivative part of that. Please try the last two. See how you do. Keep those guys up there so you can take a look at it. Give the last two a try. See how it goes. When you're done, take a peek. Again, remember the law is not that you have to bring that derivative of the inside back to up to the front, but I'm going to ask you to do that, please. Please bring that inside, the derivative of the inner part out to the front. In fact, maybe you can get into the habit of taking that part first. Take the derivative of the inside here, and then I do the derivative of the sine part of it there. How do we feel about that? Okay? Okay? Homework? The moment you've all been waiting for, right? We love homework.